Good evening. My name is Nantambi Melissa, and I am going to be presenting our slides for the Contextual Acoustic AI for generating Luganda folk music from stories and moral narratives. So these are the contents of the presentation. So for the background and introduction, I'll be defining the keywords of our project. One was large acoustic model, and this is a deep neural network that's trained on large sets of audio data, making it able to understand and generate audio and generate sound that captures the acoustic details and high-level structures of sound. And for our project, the model is trained on Luganda folk music. Then context-aware music generation is where the model is trained to adapt its music composition based on a moral theme. Then acoustic embeddings, these are the numerical representations of audio features in a compact and understandable form. This makes it possible for the computer to understand them. Then we have cultural preservation, which means maintaining, protecting, and promoting a society's cultural heritage, which in our case we are doing through the folk songs. Then Luganda folk music. This is traditional music played in the Luganda culture. Then oral tradition. This is the intangible heritage that is passed down by elders through the word of mouth. Then storytelling refers to the cultural activities of sharing stories. So the related works to our project, we saw we looked at two models that were quite similar to ours. One was the Muse Flow, which also uses a condition just like ours does, but its limitation is that it's limited to a context of genre music, unlike ours, which we have specified to be of Buganda folk music. And then as well as the iComposer, which is also a music generation system, but it's limited to Chinese music. Then we also looked at the Masakane, which is an NLP initiative by Africans, and it includes Luganda as well, but its limitation was that it's mainly for speech translation and no generative tasks are involved in it. Then we also looked at three papers that talked about the aspects of large language models, generative AI, and music generation. So our domain application problem is the loss of oral African tradition, particularly in Buganda, and it's difficult for the new generation to access this content. And so our project is aiming to preserve this and make the culture also easily accessible to these people. Then the computational problem, we're generating culturally authentic Luganda folk music from moral narratives via cross-modeling in low-resource conditions. Essentially, we are learning a function that maps narrative text, moral themes, and style constraints to lyrics, rhythm, melody, and timbre, and the result is a context-aware, culturally structured folk song. So currently, most generative music models lack cultural conditioning. They mainly focus on Western music and genre music, not specific to the African culture. Then they also use weak semantic conditioning, but ours uses moral cues instead for the music generation, to condition the music generation and where the audio features come about. But then there's also a problem of data scarcity for Luganda folk music. Generally for Luganda, for the African cultures. So our model intends to build on these current computational solutions, music generation through lyric emotional analysis, as well as fine-tuned large language models. So our research questions and objectives. So our objectives were to create data sets of both text and audio, and these would contain recordings of Luganda folk music as well as folk stories. Then we also performed exploratory data analysis on the folk stories and the local music obtained. And then also an objective was to perform exploratory data analysis on the folk stories and local music obtained. Then to evaluate models generated output for coherence and thematic consistency. And then also to propose a framework for sustainable deployment of low-resource culturally grounded AI systems in African contexts. So the research questions: what are the architectural components necessary to compose both lyrics and melodies while adhering to linguistic and musical constraints of Luganda folk music? How can our model be deployed in a constrained setting without losing the quality of generating music? Then also, how can we ensure that the generated music remains culturally faithful, specifically to the Buganda culture? And then to what extent does rhythmic variation of a song reflects the change in the narrative structure of the lyrics? So our research contributions were able to create an audio data set, and this contains recordings of songs from the Buganda culture. We also created a text data set that is made of Luganda folk stories by transcribing YouTube videos and reading contents from different folk tale-based books. Then we also created a function that utilizes the Emotify music dataset and the J. Hartman model to assign each verse in the song lyrics an audio feature. Then we were also able to generate lyrics from a folk story that the model had that one of our models had generated, based conditioned on a moral theme. Then we move on to the system architecture. So the knowledge base, as I've said, are the datasets of folk stories, folk music recordings, and then also the Emotify dataset. And from the input layer, one inputs a moral theme that's processed, that is processed to be input into the system. So the story generation module starts with text encoding for the moral theme. Then this encoded data is moved to the large language model, where the story is generated, and then the story is decoded too. And the output of this is the generated story. Then move on to the lyrics generation module, which generates lyrics from the story that was passed into it. Then after the lyrics have been composed, we go into emotion and audio feature mapping, where the lyrics are analyzed and the emotions from them are obtained, and audio features are mapped onto each of the lines in the lyrics. Then after each line in the lyrics has its corresponding audio features, we go into the music generation module that uses a conditional variational autoencoder and is able to come up with audio from the features that were described, that we had obtained earlier. Then after we have generated the audio, we go into post-processing, where denoising of the generated audio is carried out. Then after we are done with that, we move on to translation of the English lyrics into Luganda using a sequence-to-sequence model. And at the end of that all, we have our output, which is a completed song package containing lyrics and audio in Luganda and the audio as well. Then after all this, with feedback from the users, the input can be refined to be able to generate better output going forward. Yes. Then we look at the architecture for a large language model, which was one of our models, particularly for the story generation and for the lyric generation. So we start with input. Then after we have gotten our input, tokenization is carried out. Then after that, we go into embedding. Then after that, we go to the transformer block with its n layers. And from here, we start with root mean square normalization, where the input that has been tokenized and embedded is normalized from this point at the RMS normalization. Then we go into the multi-head self-attention, where we are able to determine which parts of the input, which part of the tokens, which part of them are important and how do they relate to each other. Then we go on to residual connection, which combines the input of the multi-head self-attention layer with its output. Then we go through root mean square normalization again. Then after this, we go into the feed-forward network. And here, and on the feed-forward network, we are able to, at the feed-forward network, we are, so the feed-forward network, it carries out further processing and also nonlinear transformations. Then we go into the residual connection again, which combines the input of the feed-forward network with its output. Then this happens throughout all the n layers of the transformer block. Then after this we go on to, after that, the output of the transformer block goes through RMS normalization again, then onto a linear function, which maps the tokens onto the entire vocabulary, then onto the softmax function, from which we are able to determine the next likely word from the probabilities. Then after that, we can get our output. So the mathematical formulations we considered here were the low-rank adaptation update, the grouped query attention, as well as the rotary positional embeddings. Yes. Then we move on to the architecture for the conditional variational encoder. So the encoder here takes in two forms of input, which is the conditional variable y, which are the instrument labels for the different instruments from our data set, which were the xylophone, drums, ball lyre, and the shakers. Then it also takes in spectrograms of the audios. Then and it maps, and from the encoder, these are mapped onto a latent space. Then the output of the encoder moves onto the decoder, and this is where actual learning happens. The decoder is able to map the different sound, the different outputs, the different the different instruments and audio features with their original input while respecting the conditional label. Then after this, the output from this stage is taken onto the code that is able to generate for us the actual audio that we would want, but in spectrogram format. Then the spectrogram from this part is reconstructed, and we are able to get a waveform that's the actual audio that we need. The mathematical formulations we considered here were the variational lower bound as well as the variational inference framework. So our dataset description and the EDA we had a folk story dataset of about 35 folk stories from the Luganda culture. We also had an audio dataset of about 17 instrumental audios. Then we also had story lyric pair dataset, and of these we had 5. These were pairs of a story as well as the lyrics obtained from that story, and we had 5 pairs of this. Then we also had the Emotify music dataset that had about 400 song excerpts, and these ones had the songs as well as the emotions invoked in a listener when they listen to this particular song. So from our EDA, you can see that the most common theme in the stories was wisdom, then cleverness, then caution, then obedience, and so on and so forth. You can also see that the longer stories had fewer themes, and the medium stories of between 500 and 1,000 words had an average number of themes, and then more themes in the short stories. Then from here, we can see the stories, because we have a plot of number of themes against story ID. You can see the number of themes in each of the stories represented by their IDs. Then we can also see that we had many stories of about 2,000 characters, then fewer stories on the end of 10,000 characters plus. Then here we have EDA for the audio dataset. And from here we can see that the xylophone had the most number of files, and then the bow lyre and drums. And then since our audio dataset had some audio recordings that were of single instruments and some of multiple instruments, the ones of multiple instruments that had xylophone, drums, and shakers are also represented here. Yes, then we can also see that the drums had the longest duration. Yes. Then we go on to still EDA for the audio dataset. From the heat map here, we can see that for the different audio features for our audio dataset. Yes, so from here we can see that we have audio features plotted against each other, and we can see that the ones of bright red show those audio features that have strong positive correlation. Then the ones of dark blue show those with strong negative correlation. Then we move on to the waveforms for the different audio recordings. Remember, we have those of single and multi-instruments. So those of single instruments and multi-instruments are displayed here as well. Then this is the EDA for the Emotify dataset. And from here, we can see the audio features and the emotions, but again, and as well as more audio features, because here we have the tempo plotted against the emotions that the song invoked in the listeners. Then we go into the outputs from our model. So here we have a folk story that we generated from the model when we had given it a moral theme of cleverness. Then from this story that the model generated, we were able to generate lyrics for that song. From this story, we got lyrics for this song. We got the lyrics. Then after that, we got the audio features from the audio feature mapping function that I talked about earlier. And this audio feature, and from these audio features, we're able to generate this audio. Then after this, we translated these lyrics into the Luganda equivalent, which we can see here. Then the expected results and discussion. We expected the reconstruction loss to decrease and the KL divergence to increase, as we can see from here. And then our output from the audio generation had some noise, and this was the before, and this was the after. So we carried out spectrogating to remove this noise from the audio tracks generated. And then we trained two models, one at 3 epochs and one at 4 epochs, but we chose a model that we went with the model that was at 4 epochs, because beyond that point, validation loss was increasing, which you can see from this graph here. Beyond 4 epochs, validation loss rises again, so we chose to go with the one at 4 epochs. Then we also carried out a comparison between a fine-tuned llama model and an untrained one. And from here, you can see that with the untrained model, the test loss and the perplexity is great than when the model was fine-tuned, as you can see here. Then demonstration of our developed product. Here, a user selects the theme with which they want to generate their song, and from here the generation process begins, where the story is generated, the lyrics, the audio features, the audio, and then the translation to give the full song package. So our intellectual assets, we have a modular multi-stage architecture that I've talked about before. Then also the lyric to melody mapping algorithms based on emotional analysis that I've also talked about, as well as the Luganda cultural corpus that contains the stories and the lyrics. And then the limitations we faced, we have a small size dataset of story to lyrics pairs. Then also assigning each verse in the lyrics an emotion without first considering the next ones or the ones before it brings about some misleading. Then also denoising the music samples also takes out some part of the instrumental sound as well. Then also our submodules are highly interconnected, so output quality of the previous model will affect the next one in the pipeline. Then also for our system, automated evaluation is difficult since cultural authenticity and emotional resonance is subjective to the person listening to the generated music. Then also we have a limitation of inaccurate translations of English lyrics to Luganda, which brings about loss of meaning. So to conclude, our project presented a context-aware Luganda folk music generation system that transforms moral narratives into culturally inspired songs through a multi-agent architecture. And as I've said, the work was limited by data scarcity and propagation of errors through the modular architecture. And this highlights a broader need for better cultural data representation and multimodal alignment. Future works should focus on building larger size datasets and carrying out optimization for deployment, and then also improving multimodal alignment. They should also adopt community-driven data collection as well as real-time feedback for the output they generate. And then also, since our audio recordings, our audio recordings had noise, and we recommend future works to use better technology in recording to take away that problem of noise. And these are the references we used when carrying out our work. And would like to thank the Department of Performing Arts and Film at Makerere University for providing us with audio data that we use to make our dataset. Thank you.